Go ahead.
Okay, so hello everyone. Today we'll be looking at universal approximations of invariant maps by neural networks paper by Dmitry Yarotsky. So the symmetries play important role, and especially in the machine learning context. We may have a lot of symmetries in our data that usually naturally present there, usually we may in advance know many symmetries. Maybe we are looking at images of objects, for example, and then the objects certainly do not depend on the way how they represent it as the image. For example, we may consider like different images of an apple from different angles, and an apple remains an apple. And so this is mathematically described by suitable groups of transformations that represent the relevant symmetries. And so naturally, we may prefer to have our machine learning model to respect such symmetries in a way that, for example, our model f, our function, may be invariant, meaning that if we transform the input somehow, for example, we rotate an image or translate, then the output should not change. And another type of symmetry is called equivariance, where you want the output of the model to be transformed similarly or accordingly as the input transformed. And so it is the case where we're talking about functions that map not to a scalar, but to some vector space, from vector space to some other vector space. And
so that would be like covariance, right? So...
Yeah, in physics, such things called usually covariance, right?
But more general, this map inside of F and outside, they can be different maps, right? They don't have to be the same.
That's right. This is some simplification of notations was used, and this was discussed in the paper that, of course, in input space and an output space, there might be some different transformations you may wish to have, right? Yeah.
Different, but parameterized by the same gamma, maybe. I don't know.
That's right. Yeah, that's right. They should be somehow connected through this gamma, through this group of symmetries that we are talking about. And this is important in the context of multi-layered models, where you want symmetry to propagate, where you stack your predictive layers and stream the output of one model to the input of the other model. And this is especially important in such cases, for example, with convolutional layers.
But you don't need it to actually propagate. All you need is symmetry to be inside and outside. You can have a broken symmetry in the bulk, no?
That's right. That's right. It's not the necessary condition. Yeah, but in some, well, this way you can maybe it would be easier to you to analyze what's happening in the bulk if you have this symmetry propagating inside the bulk. It just would be more convenient to for analyzing this. But yes, in general, maybe you don't need it, and maybe it would be in some cases be even beneficial to have broken symmetry inside the system, and somehow later in the output it would be recovered. Yeah. Okay. Then in the paper they discussed two types of approaches. Maybe there might be else, but in general, this seems to be two kind of pretty natural approaches. One is the symmetrization one, where you can have your model or your function not invariant, but then use kind of perform group averaging to have symmetrical function, to construct symmetrical function. And this is illustrated with the example of polynomials and with the permutation permutation of input variables symmetry. And here f, it might be not invariant polynomial, but then if you consider different substitutions of inputs in different order and you average over such permutations, then your final function would be polynomial, and it would be a permutation invariant polynomial. And presumably,
is it like proposal for the activation dynamics to be like that? Basically, you have some inputs, get some output, then you permute all your inputs, get again some outputs, and then average them out, and that is one.
It's common general approach, yeah. But for it's here it is just illustrated with polynomials, but later we will see the examples where people really did it.
That's expensive. I mean, like, you know, to
yeah, that's really it is
grows exponentially.
Certainly that's expensive. But I guess from point of view of theory, this might be an important example which you may compare with. You may construct your own cheaper model and compare it with this one and guarantee something, some convergence to this model. Yeah, something like that. So it's from mathematical theory, it might be important.
And in some case, are they constructing? I'm missing. So is this is just definition for the symmetrization, but are they constructing architectures where this symmetrization like actually happens at the level of learning or no?
Yeah, we'll see. We'll see.
Okay.
We'll see. It's just general strategies that one can perform, and usually you may not be iterating over all your group. You may just sample from it, depending on your computational resources. Okay, and then there is this intrinsic approach, which is more probably preferable than where you don't perform this symmetrization, but you have like intrinsically you have the nice properties of your functions. For example, with polynomials, there is a theorem that there are finitely many polynomials that are invariant under certain group of transformations, and then they are kind of generating polynomials. And then the claim is that any symmetrical polynomial may be constructed by considering a polynomial of these generating polynomials. But the real question is, of course, how to construct such generating polynomials, and it depends on the group of symmetries you consider, the space you work in. But I mean, it's just a general theorem that exists.
Well, it also has to be a compact and finite dimensional group, otherwise you wouldn't do it.
Yeah, and in this paper, we was talking mostly about compact groups. After Dmitry Yarotsky talked about compact groups mostly.
Okay.
And then in machine learning, we have symmetrization at the level of data set, where we use augmentation, where we have our training data, then we can enrich data set by considering different inputs that were transformed according to our transformations from our group of symmetries that we consider. And this way, we push model to learn the symmetry, because otherwise the loss of the training would be bad. And only if it learns the symmetry, if the loss goes to zero. Oh, I mean, there's some soft way, I believe, to impose such symmetry. But this is what people usually do in machine learning, common strategy. Then again, one may use symmetrization, but again, of course, it's very costly to do. But depending on your resources, you may just sample from your group of symmetries, just from some subset of your gamma, and perform this symmetrization addition. Okay, then the common example and pretty much famous example from intrinsic approach, it's convolutional neural network, and which was considered theoretically in the paper, and there were some theorems proven for this network. I will show you later, but this is the example where we have certain grid translation symmetry intrinsically, just without any sampling, without group averaging procedures, things like that. Okay. Then one of the focus of the paper was also on one hidden layer networks, and just like we know for one hidden layer network that it has universal approximation properties. There is a theorem about it. So of course you need very wide hidden layer, but there is a theorem that claims that these ansatz can approximate any function on a compact set of inputs. And then the idea was to consider how we can adjust this ansatz of just one layer perceptron to have certain symmetries. Okay, and then for this work again, there was kind of considered groups of symmetries that have a linear representation as so there is some vector space that carries this linear representation, meaning that there are invertible matrices that are representing the transformations, corresponding transformations. And that's all. The idea was to study maps from this vector space to real domain, to scalars, or maps from one vector space to some other linear vector space. Okay, then two propositions here is about how it's again about symmetrization by group averaging, basically, but just there was kind of rigorously stated statements and proven for compact groups that you can really, with the following ansatz, where you have really one layer perceptron and you consider all your transformations of inputs and you integrate with a Haar measure, and then such a function will give you arbitrary invariant map. That's kind of maybe pretty much well, again, it's not practical because this integration it may be very costly to consider really all of possible transformations of inputs before you get your output of your model.
But it's also trivial because the way you define this averaging, of course, it's going to be invariant under the.
Yeah, it would be invariant, but the important point is that it's complete. This ansatz is complete.
It's complete because of what was said before, because a single hidden layer is enough to describe.
And it's
with
really
large enough n. So it's again, and this completeness just boils down to completeness of
Sure.
decomposition.
Yeah, they are pretty much related, and I believe in the proof it was used. This result was really used. Yeah,
Okay.
that's right. And similar result was obtained for equivariant transformation or covariant, whatever you call it. Yeah, and then the idea is that just rigorously prove this, and maybe then later it can be used to prove for some other models.
But again, I will be stressing it again. Like once you know the symmetry, there is certain restrictions have to be applied to the constraint on the architecture. So that's the difficult part. Given that you know a symmetry of your input space, what are the constraints on your architecture or function f? So is this addressed anywhere in the paper, or?
Yeah. It is addressed, I believe.
Okay. Because figuring out the architecture from the symmetry, known symmetry, like, for example, you said convolutional neural network. So it has, certain constraints, convolution constraints, they come from the grid shift symmetry. So something like this, but more general, maybe would be interesting to see.
Yeah, then there was also proven the results for how to construct like with this intrinsic approach using polynomials, and the result is also pretty much straightforward, I believe. So it's based on the theorem about generating set of polynomials that you may use to construct, to consider this linear combination of them. Then you put it into your nonlinear of some function, activation function, and then again linear combination as the final layer. And this ansatz really gives you an opportunity to produce any continuous invariant map with respect to this group symmetry. And yes, again, the key thing is in these polynomials, but it was not addressed how to construct them. It depends on the group of symmetries that you consider. Yeah. And then similar thing was proven for equivariance as well. And there was also proven interesting maybe thing about the following. So if you have your representation of your input vector space as a direct sum of components with certain multiplicities, then the idea was that you may only need to construct your generating polynomials in some other space that is simpler to some extent. It's this V prime set where multiplicities are fixed, not arbitrary M alpha, but they are fixed to be this one. So, and this to some extent simplify the construction universal approximation of ansatz for continuous invariant maps. Okay, and then for the particular examples, maybe this is more important. It's the example. It was illustrated on the permutation group of symmetries, and they consider the following case, where you have your input data as a tensor product of n-dimensional space and m-dimensional space, and it is kind of, as I understand, it's when you have your data, when you have you consider a set of vectors as your input, and they to some extent they form a matrix. This X is really maybe seen as matrix of n vectors, m dimension each. And
so
maybe
it's not a vector, so it's like a matrix. It's a tensor.
Yeah. And you wish to have maybe for this task, you wish to have a symmetry with respect to permutation of rows in your matrix. And this means that maybe you want a function that acts on a set of vectors but the order of vectors, it's of no importance. Something like that. So you apply your permutations on the first index here. And there was proposed specific architecture for that, and it was proven that this gives you any arbitrary invariant continuous map with respect to this permutation of rows, first index. And they kind of, we can compare it with the direct symmetrization, which is costly and obviously where we would consider all possible permutations of our rows or columns, depends how you call it. So, and if you have n rows in your input data in your input matrices, then n factorial will be the number, the measures of the number of your permutations that you need to consider. And with large n, it would be enormous, right? But that's like 215 that was proven. It does not have this n factorial asymptotics. So it's computationally
but 215 is just 2 layers, right? So you take a matrix, or what is it?
Yeah. It's two layer network.
So in the inside, you only contract with the second index, and then in the second one, I guess. Why is this corresponds to symmetrization, automatic symmetrization, the architecture? So you're saying that this architecture has permutation invariance built in the architecture, and you don't need to do the symmetrization, right?
Yeah.
So that for that all we need to do is to permute x. You said the first index has to be permuted, yes?
Yeah. First index. Yeah.
And if you permute it, oh, okay. So how the answer should be the same, okay?
Yeah, because as other tensors, they don't have n, so it's really doesn't matter. Seems like that.
Oh, because you sum over all n's. Okay, so I see. And this probably sigma is element-wise function. Okay.
Yeah, sure. It's element-wise, yes.
And then because you okay, yeah. It's not the most general architecture that has this permutation symmetry, just an architecture that has permutation symmetry. So I mean, I can just add the first index, and that function will have this permutation symmetry, but it may be too restrictive. So this is not the most general architecture with permutation symmetry, 215.
But it's proven to be complete, meaning that any function, any black box function that has this symmetries, they can be approximated by this.
I see. Okay. Got it. Okay, perfect. Thanks.
Again, but the only problem with this paper in general that it does not show how to train such models, and is it even possible to train?
No, it's a shallow network, so it may not really converge there fast. But so right, so yeah.
But the proofs were rigorous.
Having a universal architecture is not enough. You also
for sure.
So as you said, that one hidden layer is enough, but that's not. Yeah, you're not going to converge to your solution fast. Okay. But as a universal,
it might or might not.
Right.
Yeah. Okay. Then they also considered convolutional neural networks in the paper, and the construction started where we consider the input as as the function, as an actually kind of smooth, maybe not necessarily smooth. I'm not sure, but it should be some signal. This in this example, it's one-dimensional one, and then we consider maps from function to function, from signal to signal. But of course, with convolutional layers, with convolutional network, we need to construct grid. So there is kind of projection operators that project you from your function to your grid representation of a function, lattice representation. And then pretty standard things. You have your convolutional layers, and then you have your output, and you have a certain parameters that you need to specify. For example, this lambda is like discretization parameter, how distant your grid points will be in your space. Yeah, and the group of symmetry they consider is like this shift transformations, where you kind of shift your grid or shift, well, yeah, grid or the coordinate system itself in the original space where the function phi lives. Yeah. Pretty much standard things. And then there was the theorem proven that actually is that any map from one signal function to some other single function in some other space, linear space, it's a limit point of convolutional neural network with these conditions that it should be this kind of equivariant with respect to grid translations, and it should be also be continuous. So really, the idea is that this in the limit probably of very small discretization parameter, you can really approximate by your convolutional network with enough sufficient width. You can approximate any transformation of one function phi to some other function as output. So any map.
But it's the same as what we do when we do orthonormal transformation of functions. Yes. So you can go from one set of basis functions, which may be delta functions, to other ones, which may be sines, cosines. There are many ways for you to go from one universal set of functions to the other one.
I guess the main result is just this proven theorem about this universal approximation of convolutional network for the any maps that are translationally invariant.
But then there has to be
equivariant.
Shared weights or something if we want it to be translation invariant. Then the weights in this convolutional blocks should be shared.
Of course, it is a standard. I guess it's standard thing that they are shared.
Okay, that's fine.
Then there is a kind of, they discuss certain problems that if we have pooling or something like that, the symmetry may be broken. Exact symmetry. If you drop some nodes, if we coarse grain too much, then we can lose it.
You always lose some information. High frequency modes are lost once you coarse grain. I mean, you have to lose information. So
well, Yeah. Then they also, in the sense that they also considered convolutional networks with pooling, and with particularly with downsampling, where you drop certain grid points and just keep track of your signal less frequently. And in this sense, like in standard machine learning, it's like believe padding or something, where you how frequent you shift your kernel where you do convolutions. So here you really make your steps of your kernel not just with the step size 1, but with step size 2 in this example. And there was also proven a theorem about such case as well, that this also allows you to perform arbitrary continuous map. But in this case, not from the signal to signal, you cannot do that, because here you lose at each layer, you lose information, and at some point you stuck with just a scalar. And this is mostly about kind of classification problem, probably, where you want really to predict just one particular quantity of your signal. Oh, well, it might be not classification, it might be regression, but the thing is that this map is from signal space to just one number. Okay, and then finally they considered planar motion symmetry, where you want to have, after your transformation, where you want to do distances and orientation of objects to be preserved. And this is described by this semi-direct product of translation and the orthogonal group that perform rotations. Yeah, and then here is just how the group multiplication works in such a group, and how the action of this element of a group of your transformation works. It's actually just rotate you and translate. Okay, and then for some tasks we want to have this symmetry to be preserved by the model. Then this is there was some proposition also proven that you may start with a map that is just translationally equivariant, and then you may symmetrize it by considering different rotations, and then after all you will have this symmetry with respect to both translation and rotation. And it was also proven rigorously that you can do that. And finally, the most kind of difficult part that I'm not so sure about, but there was a proposed neural network, and it was only considered in two-dimensional space with respect to this SE group of symmetry. And it was also proven that the proposed model is kind of provide you complete model to approximate any continuous and invariant or equivariant map. And cannot probably show you all the details, but the idea was that you need to consider 3 types of different transformations, and I was only be able to understand the first part where you want to smooth your initial signal or input with this operator that consists of Laplacian, and this in limit, I believe, with small lambda, where the discretization parameter is small. It's kind of corresponding to Gaussian smoothing, as far as I understand. And then there goes certain layers, and there was proven that this map will also give you any ability to reproduce any continuous in the equivariant map. Okay. Unfortunately, there were no kind of numerical results or simulations or examples how to train certain models, but a lot of theorems that were with rigorous results in terms of proofs of universal approximation properties of certain maps. Okay.
Great, thanks. See if there are questions. Can you go back to equation
no,
2?
I was just
Oh,
asking
Diego, go ahead. Go ahead.
No, I was just asking to confirm if I understood the thing. So the main idea is that it's difficult to measure some symmetries, right? So these measured instead.
Difficult to impose symmetries.
Oh,
Even if you know what they are, how do you impose that at the level of architecture?
But then you can use like another term to instead impose something conserved, to be conserved, that should be equivalent, right? Okay, so all right.
So if you go to the 215, maybe, I mean, there are many places where something appears, but I just remember 215. So basically, this is the first interior map, sigma, together with summation. That's an invariant. So basically, you form an invariant in 215. So the interior sigma map, and then summation over n. Once you summed over n, this thing is already invariant with respect to permutation symmetry. And then you can form many invariants by changing, your B's, A's, E's, sigma. Well, maybe you want to keep sigma. And then they say, okay, once I have that, out of that, I'll be out of the invariance, I'll be forming arbitrary nonlinear function. And after that, you don't need to just form one layer. I mean, you can, once you already work with invariants, with scalars, you can use them input, and then we create arbitrary architecture, and then, shallow ones like 215 will maybe not produce good convergence, although it's universal, but then you can easily add layers and make it deep or, unconstrained, whatever you want to do. But the idea is, so you want to form invariants, and then use invariants to create maps. Now, but the two questions remain. What is the right invariance to choose? Yes, because here, there is no prescription to find A's and B's or sigmas. You're just saying like, all of those will describe arbitrary invariants, but how do you actually describe them? How do you find the right invariants to use? And that's a question. And the second, once you have those invariants, how do you build network out of that? So yeah, in between, there was a place where it is clear that the map will be invariant. But it shouldn't just be invariant. It should also be generic enough so that the solutions can be efficiently found. So that's kind of the thing that's it's not here. But yeah, I agree. If you can define your invariant by just summing over all group elements, that will certainly be something that you can put into your network. But I think 215 may need to be generalized if we are to use it for in practice.
Yeah.
Just a comment, right? Other questions? But the following equation is, of course, is defining equation for the symmetry. It's really, the question is how to not do that, how to not just average over all of the symmetry group, because it's huge usually. How to move the symmetries of the data set into this constraints on the network. Okay, thank you, Yaroslav. This is very interesting.